Welcome back, everyone, to another deep dive. And today we're going to be looking into the world of perovskite solar cells.
PSCs.
PSCs for short.
Yeah.
Yeah, you've probably heard of them. They're kind of a hot topic in the renewable energy field right now, and for good reason.
Yeah, they're rapidly gaining ground and might even give traditional silicon solar cells a run for their money.
Okay, but can they really outperform silicon in terms of like efficiency and, how long they last? Silicon's been the top dog for a while.
Yeah, and it's not going to be easy to dethrone, but there is this really interesting research article we came across that tackles a major hurdle for PSCs.
Okay, so before we get too far, can you give us a quick rundown on how these PSCs even work? It can't be as simple as just like leaving some perovskite material out in the sun and boom, you've got power.
Yeah, it would be amazing if it were that easy, but there's a bit more to it. PSCs are like complex structures with different layers, and each layer has a specific job.
Okay, so like a high-tech sandwich. I can get behind that.
Exactly. So you've got the perovskite layer, which is the star player. It captures sunlight and converts it into electricity.
So that's the part that's actually like making the electricity.
Right, but to get that electricity flowing, you need something to carry the positive charges called holes that are generated by the perovskite, and that's where the whole transporting material, or HTM, comes in.
HTM. Okay. I have to admit that name always throws me off a little bit.
Yeah.
Sounds very sci-fi.
Yeah, it does sound like something out of Star Trek, but basically it acts like a bridge, moving those holes to the electrodes, which then collect the charges and create the electrical current we use to power things.
So it's like the perovskite's best friend, helping it reach its full potential.
Exactly. Teamwork is key. But here's the catch. The current standard HTM spirometad has some drawbacks. It's expensive to produce, the synthesis is complex, and it's not a fan of moisture.
Oh, moisture. That's not good for something that's supposed to be outside all the time, right?
Not ideal.
Okay.
So finding a cheaper, more efficient, and more stable HTM is like the holy grail for making PSCs commercially viable.
Okay, so that's where this research comes in. They found a better HTM.
They found two, actually, XC2M and XC2H. And get this, they're not only cheaper and easier to make than spirometad, but they also have this unique butterfly structure.
A butterfly structure. Now that I've got to hear more about what's so special about this butterfly shape, and does it have something to do with solubility? I vaguely remember from chemistry class that that's important when you're working with materials.
Your spot-on solubility is key, especially in manufacturing. We're talking about creating a smooth, even layer of this HTM on the perovskite. You want something that dissolves well and spreads easily. If it clumps up, it's not going to work well.
Okay, that makes sense. So how did these new HTMs perform in tests? Did they live up to the hype?
XC2M showed an initial efficiency of 13.5%, which is pretty impressive because that's already comparable to spirometad, which came in at 12.2%.
So neck and neck on efficiency. But what about stability? That was a big issue with the old HTM, right?
Right, and that's where things get really interesting. While XC2H had a slightly lower initial efficiency at 10.2%, its stability was off the charts.
Wait, really? So even though it wasn't as efficient at first, it lasted way longer?
Way longer. After 720 hours in humid air, think of it like a sauna for solar cells, XC2H retained a whopping 88% of its initial efficiency spirometad, only 55%.
Wow, okay, that's a huge difference. What's XC2H's secret? What makes it so much better at handling humidity?
It all comes down to its molecular structure, specifically those long hexyl chains that give it that butterfly shape we were talking about. They act like tiny umbrellas shielding the perovskite layer from moisture.
So it's like XC2H has its own built-in raincoat. That's pretty cool.
Yeah.
But it's not just about keeping the water out, right?
Right. Those hexyl chains also help XC2H form a really smooth and compact film, which is important for efficient charge transport and overall stability. Fewer gaps and cracks mean fewer opportunities for defects to form.
So XC2H is cheaper to produce, easier to work with A&D, it's more stable. It sounds almost too good to be true.
It definitely shows a lot of promise. And what's even more exciting is that the researchers didn't just stumble on these results. They did a deep dive to understand why XC2H is so stable, which is incredibly valuable for further development and optimization.
Of course, it's still early days, right? More research is needed.
Always. This is just one study. And while the findings are exciting, we need to see how these new HTMs perform in different types of PSCs and under real-world conditions. But it's definitely a giant leap in the right direction.
Okay, so we've covered the basics of PSCs, the challenges with current HTMs, and these exciting new contenders. Now let's really dig into the details of this research.
So they use this triplication perovskite formula in their
The
research.
triplication perovskite formula.
Okay, that sounds a little intimidating, I'm not going to lie. What exactly is a triplication formula?
It sounds more complicated than it actually is. Basically, it just means they use 3 different positive ions or kelpications within the perovskite structure. Cesium, formamidinium, and methylammonium. Okay, I think I'm following. So each of these chemifications brings something unique to the table, and by combining them, you can really fine-tune the perovskite's performance.
Exactly. Think of it like baking a cake. You wouldn't use just one ingredient, right? You use flour, sugar, eggs, all these different ingredients that work together.
I like where this is going. Cake analogies.
Yeah.
I'm here for it.
So just like a good baker, these researchers weren't content with just making a good cake. They wanted to understand the science behind it. Why does this combination of ingredients work so well? That's where things get really interesting.
Because anyone can get lucky with a good recipe, but figuring out the WHY, that's the real challenge.
Right. So to unravel the mystery of Xe2H's stability, they use some pretty high-tech tools like scanning electron microscopy and atomic force microscopy.
Okay, we're talking serious magnification here. Zooming in on these perovskite films at a microscopic level.
Exactly. They wanted to see how the different HTMs affected the morphology of the films. Basically how smooth or bumpy the surface was.
Because a smoother surface would mean better charge transport, right? Like a nice smooth road versus a bumpy one.
You got it. And guess what? The microscopy images showed that Xe2H created a much smoother, more compact film compared to the other HTMs. Those hexyl chains we talked about play a key role in this packing together to create a nice uniform surface.
So smoother film, better charge transport. What about the water-repelling properties? How do they test those?
They used a water contact angle measurement. The higher the angle, the more water repellent the surface.
Like how a drop of water beads up on a waxed card.
Exactly. And surprise, surprise, Xe2H had the highest contact angle of them all. So we've got smooth films, amazing water resistance.
Okay.
But did it actually translate to better performance in terms of converting sunlight into electricity?
That's the million-dollar question, right? What did the tests show?
They used a technique called steady-state photoluminescence, or PL, to figure that out.
TL. Okay, you've lost me again.
Yay. Think of it like shining a black light on a glow-in-the-dark poster. The poster absorbs the UV light, gets excited, and then releases that energy as visible light. That emitted light is photoluminescence.
Okay, and we can learn about the material by studying the light it emits.
Right, because in an ideal world, we want all the energy from the perovskite to go into making electricity, not just releasing light.
So less light equals more efficiency.
Exactly. And the Xe2H film showed the strongest quenching effect, meaning it was really good at funneling those charges towards electricity production.
That's incredible. So not only is it more stable, it's also more efficient at its main job. And to top it all off, it's cheaper to produce than the current industry standard. That's a game changer.
It definitely has the potential to be, but as with any research, we need to be cautious. There's still a lot more to learn and explore.
So it sounds like XC2H is ticking all the right boxes. Cheaper, more stable, more efficient. But I know you mentioned some caveats earlier. What are we missing here?
Well, one thing to keep in mind is that this research focused on a specific type of perovskite solar cell architecture. We need to make sure these new HTMs can perform well in other types of PSCs too.
So it's not necessarily a one-size-fits-all solution.
Exactly. Plus, lab tests are great, but they don't always capture the complexities of the real world. We need to see how these HTMs hold up long-term under real-world conditions with things like fluctuating temperatures and humidity.
It's one thing to perform well in a controlled environment, but out in the wild, it's a whole different ballgame.
Right, and while XC2H's initial efficiency was good, it still has room for improvement compared to XC2M and even spirometad.
So there's potential to boost its efficiency even further.
Absolutely. There's always room for optimization.
Now, taking a step back for a moment, what kind of impact could this technology have on the future of renewable energy if it lives up to its potential?
It could be huge. Imagine solar energy being cheaper and more accessible than ever before. We could see a significant shift away from fossil fuels and a major reduction in greenhouse gas emissions.
It's a future we all want to see. A cleaner, more sustainable world.
Exactly. But it's not just about the technology itself. We also need to consider the economic and social factors that come into play. It's a complex challenge that requires a multifaceted approach.
It's about connecting the dots between research manufacturing policy and consumer demand.
Absolutely. It's a team effort.
Well, on that note, I think it's time to wrap up this deep dive. Any final thoughts for our listeners before we sign off?
The next time you see a solar panel, take a moment to appreciate the incredible science and engineering behind it. And who knows, maybe one day soon those panels will be powered by revolutionary HTMs like XC2H.
The future of clean energy is looking bright. Thanks for joining us on this deep dive, and as always, stay curious.